Awesome. So our next speaker and our final Rising Stars speaker is Arpita Biswas. Arpita is a postdoctoral fellow at Harvard University, supported by a Harvard CRCS postdoctoral fellowship. Before joining Harvard, she was a visiting researcher at Google Research, and before that, she earned her PhD at the Indian Institute of Science. She works on algorithmic fairness, as well as problems about decision-making under uncertainty that are sort of have societally impactful problems, or that arise from societally impactful problems. And so today she's going to tell us about some of her work on fairness, in particular fair allocation under matroid constraints. So take it away, Arpita.
Thank you so much for the introduction, and thanks to all the organizers. It is a pleasure to share my research on this platform. So let me start with the motivation. So a large part of my research focuses on fair decision making, because there has been like several recent incidents where lack of fairness consideration has led to ethical and legal issues in resource allocation problems, job recommendations, and also in loan approval decisions. So this has led to escalate the necessity of fairness in decisions in general. So my research investigates fairness in allocation, recommendation, and classification problems. And presently, I've been working for providing decision support algorithms for public healthcare programs. And towards the end of my talk, I'll briefly touch upon this. For the rest of the talk, I'll deep dive into fair allocation of indivisible goods under constraint settings. So let's first look at what is a fair allocation problem in an unconstrained setting. So in this problem, we are given a set of agents, and there's a set of goods, and the values of each good for each agents are also known. What we assume is that these values are all non-negative and they are additive in nature. So the goal is to find a fair allocation where the allocation is an n partition of this set of goods m. Now the key questions for this fair allocation problems are that how do we define an allocation to be fair? And then can we show that fair allocations always exist in a particular setting? And then if yes, can we design polynomial time algorithms to obtain such fair allocations? So talking about fairness notions, the two most popular fairness notions for allocating divisible goods are NV freeness and proportional fair share. So an allocation is called NV free if every agent values her bundle at least as much as she values anybody else's bundle. And an allocation is proportional, called proportional fair if every agent values her share at least as much as 1/n times the total value of all the goods. However, it is easy to see that these definitions do not translate well to the indivisible case. For example, let's say there is one indivisible item like a laptop, and there are two students who want the same laptop. So you have to give it to one of the student, and the other student is definitely going to envy and not achieve their proportional fair share. So this has led to new definitions of fairness, which are more appropriate for the indivisible setting. And these are NV free up to one good and maximum share guarantee. So in this unconstrained fair allocation space, the results that we know about these two fairness notions are that NV free up to one good, which is EF1 allocation, it can always be computed in polynomial time. And for maximum share MMS, a 3/4 approximate MMS, it can be computed in polynomial time. However, this constraint setting is a very special case of a more general scenario where there can be constraints imposed on the kind of feasible allocations. And in this talk, we'll focus on two such constraints. One is cardinality constraint, also known as partition matroid constraint, and laminar matroid constraints. And this constraint space with these constraints were like previously unexplored. So we answer questions like whether fair allocations exist even in this setting. So let's start with understanding what is NV freeness up to one good. So an allocation is said to be NV free up to one good if for every pair of agents I and j, there exists a good in agent j's bundle, which when hypothetically removed, agent I do not envy agent j anymore. So this is an illustration of how do you show it's an EF1. So let's look at this particular allocation where agent 1 envies agent 2 because A2 is more valuable to agent 1. So this is clearly not envy free. However, this is envy free up to one good because there exists one good, which is this blue circle, which when removed from agent 2's bundle, agent 1 does not envy agent 2 anymore. So this is what an envy free up to one good relaxed fairness notion looks like. Now, keeping this fairness notion in mind, I'll get into the problem of fair allocation under cardinality constraint, in particular, Matroid constraint problem. And I'll try to describe this setting using a toy example. So let's assume that there's a museum and that wants to divide a lot of exhibits among its branches. Now, these exhibits have two natural properties. One is that the exhibits are indivisible. So painting or a sculpture cannot be fractionally allocated to any of the branches. And the second is this exhibits can be grouped or categorized into groups like paintings, contemporary art, antique pieces, etc. Now, what we consider is that these categories can have a constraint. For example, there can be natural like looking the constraint which says that no more than two paintings can be allocated to a particular branch. So given this thresholds, the goal is to find a fair allocation that is also feasible in terms of this upper limits given on each category. Now, it is easy to see that this kind of setting also captures other problems where you have to divide computing resources among various departments in an university, or allocate like medical equipment among various health centers. So this makes this entire problem really interesting and relevant. However, the existing algorithms for EF1 that obtains EF1 in the constrained unconstrained setting fails in this particular constraint domain. So we provide an algorithm that ensures that obtains an EF1 allocation in polynomial time, even with this kind of constraints. And this algorithm, the flavor of this algorithm is we look at all the items from a particular, so this category is a disjoint. That's what the partition matrix assumption is. And now we take all the items from a particular category, allocate them, ensure EF1 for that particular allocation. And after that partial allocation, we go to the next category and then again allocate them to and also ensure that after allocating every category, the entire allocation remains EF1. And the problem here is that this particular algorithm is not enough to make sure that the laminar matrix constraints are maintained. So when these categories are not disjoint and there are the categories may be like have a laminar nature, and then you cannot use the same algorithm. So for that particular setting, we propose an algorithm which has a very different flavor. So we start with an allocation which is laminar matrix feasible. And then this allocation may not be EF1. So if it is not EF1, what we show is you can always take the lowest valued bundle and the highest valued bundle and find a transfer such that the allocation moves towards being more EF1. And we show that this algorithm finds EF1 whenever the values of all the agents are identical. Informally, this algorithm makes sure that the highest valued bundle, the cardinality of that decreases by 1 after each such transfer, or the valuation of this highest bundle drops by at least a multiplicative factor of 1 minus 1 by n squared. And this helps us to show that this the iterative algorithm terminates in polynomial time, and at the end of it, it would definitely give an EF1 allocation. So the interesting thing about this result is all these results extends for even base orderable matroids, which are more general than laminar matroids. So for base orderable matroids with identical agents, we can use the same algorithm to achieve uh, EF1. And interestingly, there's a recent result by Rohr et al. Who uses our algorithm as a subroutine to obtain EF1 for base orderable matroid and non-identical, like two non-identical agents. So with this, this is an overall picture of the results for EF1 for fair allocation problem under matroid settings. And the biggest question that remains is that for general matroid within agents, does EF1 fair allocation exist? So there's no counterexample also known where we can show that it does not exist. So this remains open. Okay, so at this point, I'll quickly switch gear and I'll talk about my recent work with an Indian-based nonprofit organization called Arman. And the aim here is to provide critical life-saving information to pregnant women and pregnant women and new mothers. And the target is towards low-income communities in India who does not necessarily have access to all this information. So we are trying to see that what's the best possible way to assign health workers to this set of enrolled women in a way so that the information can be given to the woman, and the health worker is also responsible for making sure that the women are getting this information properly. They are using this information for their well-being. And some of the critical issues in this problems are that there are like millions of women who are enrolled in this program. So any solution has to be scalable. There are context-specific constraints. For example, you cannot assign all the high-risk patients to one healthcare worker. So we have to take care of that. And then there are learning components. For example, the decisions that you take right now, there are feedback which we will get eventually, which would tell us about how beneficial was this allocation or if there was any dissatisfaction. And we can use that feedback to actually improve our decisions in the future. So I have started taking baby steps in understanding how this problem would work, and I aim towards providing this decision support for socially impactful problems, and I'm hopeful that we together can help grow this space of research. Thank you. Thank you for your attention.
Thanks for the great talk.